Hello, everybody. I'm Nomin, and this is Shikhar, my teammate, and we are from Real-Time Contribution Feeds team at Bloomberg Engineering. So we are here to talk about our development project, which was about building telemetry system for our main processing pipeline. And before diving into the, details of the project itself, I would like to give you a bigger picture of what our main processing pipeline does. So our team processes subset of market data coming into Bloomberg. And here are some of the characteristics that can define this processing system. The first is the data volume, right? So our team processes over tens of billions of messages every day, and that results over 40 terabytes of data. And then you can imagine that this data is coming from quite an extensive data source around the globe. Thousands of content partners are sending us this data. And then, of course, another characteristic is high throughput. So our system processes over millions of messages per second across thousands of processes that's running on hundreds of machines, and that's been supported by thousands of connections with these data sources. Now, if I put these concepts into a picture, I guess our data pipeline looks like this. The first layer is the data source. People are sending millions of messages per second, right? And then those will be processed by thousands of processes on these machines, and then we store this data in our internal database, and from there, various applications and services consume the data. Now, with this pipeline, the goal of our project was to improve the visibility of what data is flowing through each component of this system, so that we can enhance the transparency and streamline the troubleshooting using some of the open source technologies available. So to get an idea of how we can capture that, what's happening of such a massive system, let's take a look at the life cycle of a single message. So you can imagine Bank A is sending a message about a certain security identifier that can be uniquely identified as something called security identifier. And then this message is being sent to process A in our system. Now we receive that message and processes that by the process A on machine 1. That's the unique instance of each process. And then that message is parsed and normalized and being stored in our internal database using another unique identifier, like I'm calling here internal ID. So in a way, if we want to capture these, 3 steps of a message, all we need to do is track these unique identifiers, right? So that's what we're going to do. And with these key identifiers also, we came up with some of the questions we wanted to answer using our project. For example, for security identifier, we wanted to know which instances processed this certain security identifier in last number of days, or what was the last timestamp when an instance processed it. And similar questions were also defined for other 2 identifiers as well. So in a way, this query or the question is our project scope.
Okay, thank you, Nomin. So in this talk, we'll talk about how we built this telemetry system using open source technology. And definitely gaining visibility into such high throughput systems is a difficult task. So we did it in multiple steps. We'll talk about our incremental development techniques and all of the learnings and pitfalls that you should avoid if you are trying to build something similar. So the talk is divided into 2 phases, like I said. The first part is development, where we go through the development process and our design. So starting off with the instance, like Nomin said, every instance receives data from a unique source, and that data has multiple parts. So the source where the data is coming from, the security identifier for each data point, the instance that is processing it, the instance name, and the internal ID that we map it to. We want to keep track of all this information along with the timestamp when we receive this data. So all of those unique identifiers make up the key, and the timestamp make up the value. What we do is we aggregate all of this data in an internal map using the key and the timestamp as the value. And then we periodically publish this data. Now, the reason we periodically publish it and not publish it like all data at once is because of very high volume and very high throughput. So we need to aggregate at certain intervals. And as we'll see shortly, this aggregation is what helps us stabilize the pipeline and control some parameters. Moving on, we only saw one instance, right? But again, like Nomin said, there are hundreds of instances on one machine. And then there are hundreds of machines. So it makes up like thousands of instances. So the question is, how do we stream data from all of these instances? The obvious solution in everyone's mind would be Kafka. So just connect all of these instances to Kafka and publish data. But that's really not as simple as it sounds, because doing this, we are exposing critical internal processes to an external system and hiccups and all of the downtime that might come with it. And also, Kafka has an upper limit on the number of concurrent connections you can make. And given we have thousands of such processes, it's just too many connections to Kafka. So what do? We use an open source library called ZeroMQ. ZeroMQ is a universal messaging library, and it provides abstraction on top of sockets to carry out end-to-end message delivery. And it comes out of the box with popular patterns like publisher, subscriber, client server, push-pull, all of that. And it carries messages across many different protocols, in-process, IPC, TCP, UDP, WebSockets, a lot of them. So we used ZeroMQ. And the documentation for ZeroMQ is absolutely amazing. It gives you like a lot of patterns pre-built. One of those patterns is called the router-dealer pattern. What it does is it takes data from n incoming connections, and then you can just send it out through X workers, or X connection in this case. So you could effectively control the number of connections for the incoming data point. Now, what we did is we created a proxy process using ZeroMQ and this pattern. And this proxy process is the one which gets data from all of the instances on a machine and then forwards it to whatever streaming solution that we use. So what does this do? It solves our problem because it delegates the responsibility of publishing data to another process. And then it allows us to control the number of external connections from every machine. And because it's like very thin layer on top of sockets, the library is quite fast. So it's as good as the process sending it through. And now, as you can imagine, streaming messages is pretty simple. All of the instances and all of the machines, they talk to a proxy process. And then that proxy process forwards the messages to Kafka. And finally, we did the publishing, but we also need to consume those messages. So we have a lot of consumer process, which we deploy on Kubernetes to consume from Kafka. And then why Kubernetes, you may ask? Because it's very easy to scale. We can easily add more instances. We can allocate resources. The deployment cycles are quite quick. So it's perfect for a system where the load can change anytime. OK. Going next, now we do need to store this data as well, right? We have been streaming it. So Nomin will talk more about how we store it.
Yep. Yeah. So when, I guess, going into this project from the beginning, we wanted to optimize for its high throughput and scalability in general. So one of the options we had was Cassandra, because as shown in this graph from the Cassandra documentation, it promised it can scale linearly, starting from few nodes to thousands of them. And for the first round of the project, we followed, I guess, the basic guidelines to design our schema. The first step was collecting our query patterns, and I think I mentioned this in the beginning. We will be querying by these three identifiers, right? And the second step is usually defining the tables per query. So in this case, we are maintaining these three tables. And then next is about the primary key. And for the first round, we are just simply putting the same identifiers as a partition. And then second column is date, because we wanted to do some date range queries as well. So with that, we have our complete telemetry pipeline, starting from the data source all the way to the data sink. But did it work? Unfortunately, no.
Yeah, I think like the slide said, it would be magic if it worked for the first time, right? So moving on, we move to the second phase, which is stability. Now, this pipeline may look pretty straightforward, but there are quite a lot of variables in it. Like first is definitely the publishing frequency. How often do we need to publish data from every instance? Then the number of workers. So we talked about the CMQ proxy that reduces the number of external connections, but how many connections do we want? And then the routing key within Kafka to balance the load within each partition. How many partitions should we have for all of that data? And then within Kubernetes, how many consumers should we have? And what about the resources, threads, writer threads allocated to every consumer? And finally, what should be the cluster size of our Cassandra deployment? What should be the primary key? Like Nomin said, we only had the very basic idea. So is it optimal? Is it performant? We don't know. So starting off, how did we configure these parameters? The publishing frequency and the number of workers. We use something called feature flags, which we can easily use to configure certain values at runtime. And tweaking those values effectively change the behavior of publishing and the number of connections as well. So that was quite simple. And then we iterated multiple times and observed certain key metrics while changing these values, which was CPU and memory utilization for the proxy process, and the instance to proxy latency, the failure rate of publishing to the proxy. Because you can imagine if you have less workers and a lot of load coming through, the proxy will just be a bottleneck, and there might be failures in latency. Next, for Kafka, choosing the routing key for us was simple because we wanted an even distribution of data within the partition. So we just let it to be round robin. For the number of partitions, we increased it gradually. And again, observed certain key metrics like the size of the partition, the resources that Kafka is consuming, and overall, how stable this entire setup is. Moving on, controlling the writers. Within Kubernetes, we again used feature flags to control the number of threads that every consumer has, because it's very easy to overload Cassandra if there's no limit on the number of writer threads, even though Cassandra is very performant in terms of write. And for the number of consumers, because it was Kubernetes, it was very simple to just increase or decrease anything. And now we iterated again a couple of times, changing these values, and observed the CPU and memory usage of the consumer processes, the write throughput, and definitely the Cassandra stability, because like I said, you can very easily overload it, or you can underutilize it. We also monitored back pressure within Kafka, because you have to have something in place to make sure that the speed at which you are writing matches the speed at which you are pulling data from Kafka. Now, moving on, finally, the cluster size and primary key was quite challenging, and Nomin can talk more about that.
Yep. So some of the Cassandra optimization iterations we needed to do. To understand those, I think we need to take a look at how requests are being handled by Cassandra in general. So here the client is sending a request with key 1 and value 1, right? And it reaches to one of this like a query coordinator, and that node decides which node it should go to. In this case, it's going to node number 3. So this is how Cassandra allocates their requests. And with this allocation mechanism, what could be the issues, right? So the first one we observed was something called hot partition. So you can imagine multiple requests coming in. And, depending on the value, it's being allocated to different nodes. But also it means that sometimes most of the requests are being handled by certain nodes among these cluster nodes. And here we're calling that busy node as a hot partition. And these can result into some implications, right? First, it can overload only the subset of the nodes, and it would lead degraded, performance, higher latency, more timeouts, delayed recovery, and the scaling will be just difficult. Now, to even out this, I guess, load, we needed to introduce this synthetic ID called bucket ID. So we are using this bucketing strategy. And another pattern or behavior we observed is called partition is go. It's related to the hard partition, but a bit different because it is more about the story side of the thing. So based on how you define the cardinality of your data table, most of the data can also end up in certain, I guess, nodes, and that node becoming bigger and bigger. And we observed this behavior mainly for our instance table because the number of security IDs each processes are processing varied a lot in our case. Some of the processes had only a few security IDs, while others had millions of them. So we need, again, these can cause uneven disk usage and also similar performance implications as well. And so we needed to even it out further. And in that case, we are using same bucketing strategy, but with date. And of course, another aspect of, I guess, Cassandra is the cluster size, right? We needed to adjust our cluster size in total 3 times while monitoring some of the Cassandra metrics. And in our case, we observed mainly 3 aspects, I guess. The first one is, of course, related to the hot partition and partition skew, so the data distribution and storage side of the metrics. And the second was more about the throughput and the latency of the system. And the last one was more about the general overload of the system, which can be expressed by thread pool and pending tasks. So yeah, after some iterations, as a result, we were able to achieve the throughput we initially wanted. And now we have a system that's optimized and stabilized after a few iterations of parameter tuning in a way. And now our team is also onboarding new type of metadata to the same pipeline. And we also did a lot of stress testing as we progress. So we have some confidence in scaling as our data grows as well. And key takeaway. So I think looking back, one of the key lessons for me was like the importance of configurable system plus very clear definition of metrics and what we want to monitor, right? Because you start the project, you have these initial assumptions about the project, maybe the throughput or the volume, but then they can be a bit different than your expectations. Sometimes the requirements can be adjusted as we progress, or the actual performance of a component can be different from the documentation, right? So under these uncertainties, I think having that control over all those parameters that can dictate the behavior of a pipeline makes things much easier. It means a shorter, easier testing cycles, so we can tune those parameters easily, quicker adaptations, and in our case, it reduced a lot of code changes, need for code changes or the number of deployments, and I think it just better supported the developer troubleshooting process. But yeah, that was the end of the presentation. Thank you for listening. And do we have time for a Q&A? I don't know. Okay.
We have time for one question. Is there any question in the audience or from the online community? Three, two, one, sold. Okay. Then give another round of applause for the speakers. And yeah, thank you very much.
Thank you.